Okay. First, thank you all for coming. And thank you to PHP Yorkshire for accepting my talk. I was here last year as an attendee for the first time, and so I'm back this year as a speaker. It's really, really good. I'm really proud. So the talk, my talk is called Build Your Own Neural Network with PHP, and today we are going to build an artificial neural network from scratch using good old PHP. First, it's just wondering who's using machine learning? 1, 2, 3, good. Who's using machine learning production? 1. So you already know about this stuff a lot more than I do. So let's just start with a few things about myself. My name is Vitor. You can follow me on Twitter using the handle NoiseLabs, and you can send me a direct message. But nowadays, I'm just a retweet machine for Brexit-related news, so just avoid me for now. You can read my occasional blog post at noiselabs.io, and now a few disclaimers. And the first one is that I'm not an expert in this field. I'm not using machine learning production, and so I will not be able to give you industry advice. I just consider myself to be a student. And second, there will be math throughout this talk, or to be more precise, oversimplified math. And I hope it's not too scary. I hope you don't leave the room in panic. Please just stay till the end. And third, there is a lot to cover in this talk, and in just 45 minutes. So I'm going fairly quickly through the talk. But if something is not clear, please just raise your hand, and I'll try to clarify as I go. Okay? Okay. So the reason why I'm giving this talk about AI and machine learning is because it's all the hype these days. I mean, you can barely go one day without seeing news of machine learning on articles on the web, on TV. It's just everywhere, and it's kind of magical. So I guess the only thing more hype than AI these days is blockchain. But about blockchain, I know pretty much close to nothing. So you're better off asking this guy. He's not too far from us. The second reason for me for giving this talk is because it's a bit rare to see PHP articles and machine learning together. So, and I think we deserve our fair share of AI in PHP world as well. And if you're going to learn something new and complex, such as machine learning, I think it might be a good idea to just pick a language you're already comfortable with, and then focus on this new complex thing such as machine learning. And that's why I'm picking PHP in this case. It worked well for me. Okay. So AI, you can see it being used on speech recognition. You know Alexa really well. On automated trading systems, on handwriting recognition, and the recommender systems that you can see on Amazon and on Netflix. It will soon be driving us everywhere, just like Chris mentioned in the opening talk. Maybe this is the next car that Chris will get. It will be our doctors, it will be our lawyers, and it will even write our own code. Oh, by the way, this is a pretty cool article. There is a link at the bottom. Check it out. It's a really good project. And if you have enough free time on your hands, why not place Nicolas Cage's face on films such as Indiana Jones or even Lord of the Rings? Surely an instant classic. Okay, so at the foundation of many of these applications that we've seen before, we have artificial neural networks. So today in this talk, what we're going to see is why are they called neural networks? How do they learn? How can we write one using our favorite language? And what is deep learning? So without further delay, let's start with the light topic, the human brain. And the human brain, this is where neural networks get their name from, because they are inspired by the human brain. And so this is a picture of a brain, or half of it. And in a full brain, we have 86 billion neurons. And the neuron is the basic computational unit of the brain. So this is a picture of a neuron, which is a cell. And you can see our dendrites connected to other neurons, where the chemical and electrical signals are transmitted. Then they go through the cell body and the nucleus, where they are processed, and then they flow through the axon to the next chain of neurons. Another way to look at this is if we consider our dendrite to be performing some sort of input, to be the input to our neuron, and the nucleus is now an activation function, and the signal going through the next dendrite through the axon is our output. So in 1943, McCulloch and Pitts, inspired by this biological neuron model, they developed a mathematical interpretation for that neuron, and that became the first artificial neuron. So we can see that interpretation in this way. So let's say now that we have our inputs, and I'm going to use this notation. So I'm going to use x for our inputs. So we have two inputs, x1, x2. And then we have weights. And those are attached to each synapse, to each connection between neurons. And within the cell body, within the neuron, we are performing this mathematical operation. So we are doing a sum of the weights times x plus a bias term. Okay? And yeah?
What's B?
It's the bias. I'm going to explain it in the next slide. So the weight and the bias, they are the learnable parameters. So the weight, they represent the influence of one neuron on the next one. So the strength of that connection, the synaptic connection. And the bias term is a mathematical term that allows me to shift the output signal from the neuron left or right to better adjust to my desired output. So this is the full picture of the neuron. And once I have that signal processed, I get my output, which I'm going to call A. So in summary, this is the sum of Wx plus bias. I'm going to start in a variable called Z. And my neuron output, after being passed through the activation function, F, that will be my A. So this is what's happening inside the neuron. So the activation function, it models the firing rate, and most importantly, it gives the network a non-linear capability. And this is really important. We're going to see this later on the talk. So a very, very common activation function using in neural networks is called the sigmoid function. This is this S-shaped function where large negative numbers will give an output of 0, and large positive numbers will have an output of 1. So all the output from my neuron will be between 0 and 1 using this activation function. So if you have another look at neuron, and if I zoom out, I can see my very basic neural network. And this is already an example of a neural network with one neuron, my two inputs, and one bias term. Now, it's all good. But it's missing a trick. How does it learn? So we need to add a secret ingredient to this. And that secret ingredient is machine learning. And specifically for today, we're going to have a look at supervised machine learning, which is learning from examples. So a bit of a definition. In supervised machine learning, we're going to have a data, our input, x, and we have our known output. So we already know the output. And then the goal is to learn a function that maps that x into that y, that output y. So that when we receive new data that we haven't seen before, we already have a function there, and we can make a good prediction. Well, we hope it's going to be a good prediction. And this is a departure from traditional programming. So in your programs, you're going to write the rules for that program, then you feed data into your program, and you get an answer back. But with machine learning, you're going to feed the system with the data, with the answers, and then you're going to ask the system to figure out the rule. And I think that's pretty neat. So if we have a look at our network again, our very simple network with just one neuron, this network can solve simple problems. So it can solve linear problems such as this one, such as finding this function and then predicting this new value. But most problems are non-linear. At least the most exciting ones are non-linear. So we need to upgrade our network. And we're going to do that by adding a hidden layer. So with a hidden layer, we get a network like this. And the reason for this is that when the activation function is nonlinear, such an example of our sigmoid function, the S-shaped function, which is nonlinear, and when we have a two-layer network, and here the hidden layer and output layer are the only ones that count as layers. Funny enough, in the literature, the input layer doesn't count. So 2 layers is 1 hidden layer plus the output layer, at least. If we have that, then we can say that the network is an universal function approximator. It could resolve, in theory, any function. And that's what makes them really, really powerful. Okay, so training approach for supervised machine learning. We're going to start with random weights. Then we're going to make a prediction, an initial prediction, based on the data that we give to our network. And then we're going to compare that prediction with the output that we already know. Okay? And then we're going to adjust the learnable parameters, W and B. And finally, we're going to keep adjusting those parameters, W and B, until our output is really close to our prediction. So this is the overall training approach. So let's say that we're going to build a cat classifier. We have this nice picture of a cat, and what we're going to do is we have our network. We're going to pick a bunch of pictures of cats, and we're going to label those pictures with 1. 1 for being true. And then we're going to pick pictures of something else. Could be dogs, could be cars, could be wherever you want, non-cats, and we're going to label it with a 0. Okay? And then we're going to feed those pictures into our network. We already know the answer, and we'll keep training the network until the answer is really close to being a 1 for a cat or a 0 for a non-cat. And this is the approach that we're going to use. Now, I'm afraid I'm going to disappoint you, because this is just a 45-minute talk. So we're not going to build a cat classifier. We're going to build an XOR. Quick recap of the XOR. Equal inputs will output a 0. Different inputs, 0, 1, 1, 0, will output a 1. So this is what we want our network to learn, is to learn our X and figure out the Y. So if I put this on a chart, you can see that there is no way that I can draw a line, a straight line, to separate my 0s from my 1s. That means one single neuron is not enough. This is actually a non-linear problem. So I need to go from this to this. And now, as you can see, I have fully connected neurons, okay? All affected by a weight in my hidden layer. And then the full network will look like this. And this is the network that we're going to build today. Any questions so far?
When you say adjust the weights and the biases, how do you decide what adjust means?
I'm going to show you that in a few slides. Okay, so this is the network that we're going to use to solve our XOR problem. 2 inputs and 1 output. So without further delay, let's see some beautiful PHP code. And just a note, all of the examples I'm going to show you, they are available on this repository on GitHub. So there is a lot of detail in those slides, so don't worry too much. You can check out this repository, have a look at yourself. Everything that I'm going to show on the slides is in this repo, and it's just open, it's free. Okay, let's start with something simple, with something basic, predictable, right? Let's write a class called neural network, and in this class, we're going to have 2 methods. One for train, for the training process, and one for making predictions. The train will have inputs and outputs, prediction, just one entry for the input. In our example for the XOR, we have 4 inputs, and we have the corresponding targets or outputs below. So let's just start by instantiating our neural network, which does pretty much nothing at the moment. And let's move on to defining the network topology. So like we've seen before, we're going to have 2 inputs, 1 hidden layer with 2 hidden neurons, 2 layers, the hidden and output, and just 1 output on the way out. So this is our topology. And now for the parameters. So what I'm going to need is I need to store parameters for W, for B, for Z, and for A. All those parameters that you've seen in the original slide with a single neuron. It's just now it's an array because I need to store that for every single weight on the network. And I just set that as my parameter P. Now, I could be using arrays and nested arrays to store all of this information, and I did that. It is a nightmare. There is a much, much better way to store this information, and that is a matrix. So by using a matrix, you define your variables just like this. So in a first row, you can see the weights coming into my first neuron. Second row, the weights coming into my second neuron, and then the bias. And then for the output layer, just 1 row for the 2 connections coming into my neuron. So now I have my parameters W and B, and I'm not going to build my own matrix in this talk, so I'm just going to reuse this library called math.php. There are a few good libraries for PHP, for scientific calculations, for math. So I'm just going to use this one, it's quite good. And using this library, I just define my array, which I then pass to my matrix factory, so I get the matrix back. And then once I have a matrix, I can add matrices, I can multiply them, and I can do this operation called Hadamard product, which is an element-wise multiplication. And finally, I can go to each element in a matrix, and I can apply a function to my liking. Okay. Now, just a quick note about vectorization. Other languages and libraries such as Python and NumPy, they offer vectorization, which is a very efficient way to do things such as matrix multiplication. To the best of my knowledge, PHP doesn't offer that. But I found this library called PHP SCI, and it's now 1 year old, and it offers a PHP extension in which you can perform very quick operations on matrix multiplications and arrays. So check this out. Maybe there is some hope with PHP in machine learning. Okay, next step, the activation function. So just sigmoid function, this function is defined by this equation. So what we have to do is just transform this into code. So let's create a sigmoid class and define our sigmoid method, which just does the equation that we've just seen before. And I'm going to place it in a namespace, an activation namespace. And the reason for that is that there are multiple activation functions. You can play with different ones. I'm just going to use the sigmoid today. And then I'm going to call my compute method, which is basically go to each element in a matrix and calculate the sigmoid right there. That's what I'm doing. So now I have my sigmoid class, my activation function, and I inject it into my neural network. And this is the activation function that I'm going to use throughout. And now for the training part. And for training, this is the algorithm that I'm going to use. Okay, first I'm going to initialize my weights and my bias. And then on the loop, which stops if my network error falls below what I'm going to define as the max error, or if it reaches a maximum number of iterations, because sometimes, or quite frequently, neural networks fail to learn and they go on and on forever. So I need to put a limit on that, and that will be my max iterations. So within that loop, I'm going to look at the training examples, and for the XOR, I have 4 training examples. And for each one, I'm going to do 4 operations. Forward pass, computing the cost or the error of the network, then something magical called back propagation, and finally, adjust my weights and bias, and then keep going. So this is the algorithm that I'm going to do. So first step, initializing the parameters. So I'm going to write my function, and in here, what I'm going to do is I'm going to set my bias to 0. And I'm going to set my weights to a random number between 0 and 1. And this is just best practice when initializing a neural network. We need random numbers. So I'm going to use 0 and 1 because that's the output for my network. And for the output layer, exactly the same operation. Bias are 0, and weights a value between 0 and 1. So I'm just calling that on my constructor because this is only executed once. I just want to do this one time, and once I do that, I may end up with something like this. So this is my network with random weights, my bias sets to 0. This is the very first stage in the learning process. So moving on to the train method, which is one of my 2 public methods. First, I just convert my inputs to matrices inside, so I can just work with matrices, inputs and targets. And then I'm going to define some defaults. And the default, I'm going to put 20,000 iterations. And I want my max error, I want my network to keep training until it falls below 0.001. That's when it stops. And my initial error is going to be infinite. So this is what the train method will look like with my 2 loops already defined. So now let's implement our initial step within that loop, which is called forward propagation. And here comes the math. No one left the room yet. It's good. So what I'm going to do is I'm going to apply that very same equation that you have seen on the initial slide on the neuron, just in matrix formation, matrix notation. So that's a general rule, which means for the hidden layer, I'm going to use X over there. And for the output layer, I have A. And A is just the output from the previous layer. It just goes in a chain. Input from one layer, the input from one layer is just output from the previous one. So that's the rule. So if I start writing this, I'm going to just put index 0 is going to be my input for the network, and then in the loop, going through all the layers, I'm going to do this operation using matrices. So I just calculate Z, And then I call my sigmoid function on Z, and I get my output for that layer. And the very last output is going to be my prediction. So now I have a two-forward propagation path, which is just going from input through each layer until I reach the end. So here we have our first step done. And once I've done that, my network says that the output is 0.61. And if you remember, my result should be 0. So it's quite far. Not really good. So let's see what the error looks like. And for this, we need to use a function, and it's called a cost function. And I'm going to use something called mean square error, which a quite easy cost function is just the output minus the prediction squared. So it's always positive, just the difference squared. So if I implement this, again, I'm going to put in a namespace called cost function, because there are multiple choices. You can use different ones. Different examples may require a different cost function. So compute is quite easy to do. I'm setting my constructor, and here I have my cost function defined. And now I can call it as my second step. And I'm going to keep track of that in my costs array. So if I apply my cost function, I can see now that my error for the network is 0.38. And I want it to be below 0.001. So what I'm expecting my network to do over time with training is a very high error, because it's just randomness at the beginning. And as you start to adjust parameters, it should fall below and should stop over there. That's my expectation. That's what I hope it's going to happen. And in order to do that, we need to apply something called backpropagation, which is the most mysterious step in the learning process. So backpropagation is a learning method for supervised machine learning using this kind of network, which is called feed-forward network. There are other types. And it's using something called gradient descent, which looks at the error of the network and then looks back. And it's going to use something called partial derivatives. Don't worry, it doesn't get worse than this. So partial derivatives is just a way to look at each individual parameter. So I'm going to have to look at each individual learnable parameter, the weight and the bias, and see how much that parameter has contributed to the error. So that's what I'm going to do. That's what I'm going to do with the partial derivative. Look at each individual parameter and see how much it affected the error. So I can, if I make an adjustment, does my error get better? That's why I'm using partial derivatives. Well, that's why backpropagation is using it. So these are the equations for implementing backpropagation in this network. First step, with backpropagation, we start on the output layer, and then we go all the back to the beginning. So it starts at the end. We look at the loss function, the cost function, and then we calculate dA. We call dz by taking a partial derivative of the sigmoid, and then I calculate dw and db. And same goes for the hidden layer. Only difference is that dA is calculated with dz, which was taken from the previous step. So this is just what I need to implement, again, in PHP to give me the backpropagation step. So I need two new variables, dw and db. So if you have a look, our cost function, the derivative is simply 2 times output minus the prediction. So what I'm going to do now is just add a new method called differentiate. Just subtracting output and multiplying by 2. So now I have a compute for the forward pass, differentiate for backpropagation. My two methods on each cost function and activation function. And for the sigmoid derivative, it is simply the sigmoid times 1 minus the sigmoid itself. Just repeating, if I do that using differentiate, for each element in the matrix, I'll calculate the sigmoid times 1 minus the sigmoid. So now I have those two methods that I can use. So let's start with the output layer, which is slightly different because the A is just calculated in a different way. That's what makes it special. So I just use the derivative for const function. Then I calculate dz, dw, and db, all using matrices. And then if I move to the next step, for the hidden layer, or any number of hidden layers, it doesn't really matter. I'll calculate dA, dz, and again, dw and db. I know it's a lot to process, but it's just a way to implement those equations that I've just showed before. So now I have my do backpropagation method implemented. And finally, I'm going to update my parameters. And to update my parameters, this is the last equation that I think you're going to see. And it's a way to update my weights and update my bias. So what I'm going to do is, I'm going to pick the current value for the weight, and I'm going to subtract dw, I just calculated, times alpha. And alpha is called the learning rate. Same equation goes for the bias, where I just use dB instead. So the alpha is called learning rate, and it allows me to control the jump on each step. So you don't want a learning rate to be too big, or it might jump a lot and miss the optimal value entirely. Or if you use a very low value for the learning rate, it may take a long time to learn and even fail again. So there is an optimal value for the learning rate. It's something that you can play with. So that's what I'm going to define. I'm going to use a default value of 0.1, which kind of works well for this kind of network. Last step then, update parameters. Going through each layer, I get my new W, which is current minus dW, and my new value for B. So I've just updated my weights and my bias. I've gone, so that's my last step here. And then I keep just track of the error for this network, for this pass. So this is the full implementation for my training method for a neural network. And I guess you're as exhausted as me after this. Any questions on this? Okay, so I'm going to move on just to do a recap of the algorithm for training. So what we've done was initializing weight and bias, looping until we fall below a desired error, or if it fails, stop iterations, go through each example, and then do those 4 steps. And this is the algorithm for any feed-forward neural network using backpropagation. So hopefully, what's going to happen during the learning process is my network, over time, it will learn how to differentiate my zeros from my 1, and you can see the connections between neurons to be increasing or decreasing. So that's the way the weights increasing or decreasing, because each neuron is specializing in a different characteristic. And this is also something that you can actually visualize on a network to classify images. You can see that in those kind of networks, you can see each neuron specializing in something like vertical lines or the hair of your collar. You can see each neuron specializing in different characteristics, which is quite cool. So this is what I'm hoping it will happen. So if we put it to a test, we get a high error at the beginning because it's just randomness, random values. And as we go and start adjusting our weights and our bias, the error will start decreasing until it gets really close to my desired error and stops training. So in my example, I stopped training around 10,000 iterations. And now, if I ask it to make a prediction on some values, and I'm going to cheat here because this is simple example, I don't have new values, but I should use new values for this. So I'm just going to reuse that. And to make a prediction, I just need to call my predict method, which simply calls do forward propagation. So at this moment, weights and bias, they are frozen. They are at that optimal value. I don't want to change that anymore. I'm just going to feed it new data and ask it to make a prediction. I've just finished training my network. So I'm going to give it a 0, 0. And I get the value, which is 0.03, which is really close to 0. Same goes for the 1, 1. So I can say with confidence, yes, it learned to recognize my 0, 0 input. And if we do the same, I see 0.96 and 0.969, really close to 1. High confidence, this is a 1. So my network has just learned how to recognize a XOR. So few ideas for you to apply with this. I would say pick something more challenging, pick something different other than the XOR, but this is a good start. You may experiment with different activation functions. There are a lot of different activation functions, so you can play with that. And cost functions as well. Even the learning rate, you can increase it, decrease it, and see how it goes. And if you do that, send me a PR. And just try with more hidden layers, perhaps, different topologies. See what happens if you just add 5, 6 neurons or 2 layers, see what happens. And if you're really into this, there is a competition. You can earn actually money on that called Kaggle, for where you can use neural networks. So why not do that? Okay, so recap. Neural networks are inspired by the human brain, even though nowadays it's more of a engineering and mathematical exercise using machine learning. The network I showed today is called a feed-forward network, but if you're using something for image recognition, you're going to use something called convolutional neural networks. For speech, recurrent neural networks. Each different problem requires maybe a different network. And today we saw supervised machine learning, where it learns from examples. So data is paramount here. It's really important. We need loads of data and labeled data. Maybe that's why you're solving all of those captchas. And there is another example where we have unsupervised machine learning, where it just learns from, it doesn't have a label, so it just tries to find patterns in things. That's another kind of machine learning being used. And we saw that backpropagation and gradient descent is used to find the optimal value for the weights and bias. This is the most, I would say, the most magical thing within the process, but it's really just a bunch of math. And in theory, can approximate any function, and that's why they are so powerful and so used these days. So you saw this network with one hidden layer, but if you add more hidden layers, or even more hidden layers, or even more hidden layers, then pat yourself in the back because you're doing deep learning and you're in the cool kids club. So before finishing, just a few resources that I'd like to share. Good article on Wikipedia. There are a couple of really good courses on Coursera. And this specialization about deep learning. Easy stuff to follow, really good if you're interested in this. The original articles by Jeffrey Hinton. There are some good resources as well from Google. And this is really good to read about backpropagation in more detail. But if you go online, nowadays you just see loads and loads of resources about machine learning. There is loads of stuff now. This is not a PHP book, but if you want to play around with examples, it's using TensorFlow. And there are loads of examples. I recommend this as well. And if you're in a rush, this is a video from Andrew NG, which is kind of a big star in AI. And it's just a 4-minute video, which explains neural networks as well. And with that, that's the end of my talk. Thank you. I think I have time for... Good.
You get an error, the error rate goes up or down. What does it mean to have an error? How does the network know this is or is not an error? Just define error.
So the error is calculating because you know the answer already.
Yeah.
Okay? You know the answer. So in the XOR example, you have 0, 0, and you know the answer is 0. That's my answer. And if you get an output of 0.6, your error is 0.4 squared. That's the error. But it's true that it may go, it's not straightforward because the error can be decreasing and suddenly can increase again. And that's because of gradient descent. Gradient descent takes derivatives to try to find the optimal value. And actually the graph from a cost function is not something like this, where it just stays here. It can have local optimum, and then the best one can be found here, and you can just miss it. You can just stay at this one thinking, oh, this is the best one.
Is it typical to know the answers before you start?
In supervised machine learning, yes.
Okay, because I didn't think that you knew whether it was a cat or not. I just thought that you were, you know,
yeah, the most common is supervised machine learning, and that's why I say you need loads and loads of data, and you need to give it the answer. So there are even companies.
And after you don't have to give it the answers because it understands the process.
For each example, I need to give it the answer.
Right.
And there are even companies making money right now just building data without solving any problem. Just going, getting data and saying this is it, this is that, and then sending that data to other companies to work on a different problem. So data is critical for this.
I had lots of photographs of cats, and I want to run it through this, maybe not using supervised, and then it would tell me is it a cat or not. Would you use the same approach, or would you have to use a slightly different one if you didn't know? I know you're trying to train the network, so you have to give it things that you already know the answer to, but what about just saying is this a cat or not, right?
Not with supervised.
Okay.
You would have to use something else.
Your visualization towards the end there, with the showing the graphs and how it trends over time.
Uh-huh.
Quite a few slides back, but yeah. What tool was that?
Sorry, which one?
Keep going back. It was basically your animation where you showed the different neurons and then you showed the different
I think
pathways.
where the epoch went up on the
Yeah, they had epoch
screen.
counting up at the top. That's the one.
Yeah.
What's this?
Oh, this is actually from the TensorFlow playground.
Okay.
So TensorFlow is a Python framework.
Is there a way that you would handle, obviously, your XOR situation is quite easy, the training data is very simple. What tools are there to actually manage how you train your data and store your outputs from your PHP neural network? Are there tools that wrap around what you're writing as code to manage the data and manage the outputs you get? Because I imagine some of these might take, rather than seconds, might take hours or days
Yes.
or
Yeah.
to run. What tools are there that exist to make sure that you can capture that data and store it somewhere and view it and visualize it?
To be honest, I'm most familiar with some Python tooling other than PHP. But there are plenty. Actually, if you use TensorFlow, if you use Keras, if you use, what's it called, PyPlot, PySci, something like that. You can actually chart some graphs. You can see what the network looks like at each moment. If you go and check out the repo, the GitHub, the PHP repo for this talk, what I built was for each step in the learning process, I'm printing out the values and building an HTML page with that.
Okay.
So you can actually see over time what's happening to each weight, and each the error. So it helps me debug what's going on.
Cool.
But there are a few tools.
Great, thank you.
Is there a reason why this took off in Python rather than any other language? Is there anything intrinsic to Python that makes it efficient?
So I would say vectorization plays a part in this. It's more efficient to do that using, for instance, Python and NumPy. PHP is still good if you want to use it for online machine learning. So let's say that you're going to you're going to train a network, which may take a long time to learn, right? And once you have those optimal weights and bias, once you have that, you can use for online learning where you feed it one example at a time. So let's say a user uploads a cat picture into a website. So you just feed that one example to something that was already trained. Then you can use PHP pretty well for that because performance is not a problem. Actually, there is something called transfer learning, and there are some other types where you can use where you just pick something that was already trained. You don't have to do it yourself. You just give me the topology, give me your weights, and I'll play with that.
So then the expensive part of all this is just the training. If you have your numbers, you can port that over to any language and it'll run super fast no matter what you do.
Yes, indeed. Yeah. Because the forward propagation step is not that expensive. It's just one example. And I'm using 4 examples here, but in real world, you would feed it with thousands of a data set with thousands of examples. And you would even use something called batch processing, in which you would give several examples at the same time, taking advantage of vectorization. That's one way to do it. But there are so many combinations that you can play with. What's your batch size? How big is it? How do you want to play it? What activation? So for each layer, you can use a different activation function. And you can, in my example, I'm using one neuron for the output, which is using something called logistic. But I could use something like 2 neurons. One that will give me the answer for 1 or true, and the second one will give me the answer for 0. And if you see something like an exercise where you recognize digits from 0 to 1, from 0 to 9, you could get 10 neurons on the way out. And which one will tell you, oh, I recognize number 7. And that's the neuron for recognizing number 7. So for classification problems, if it's binary, you may end up having 2 neurons, for instance. The example I gave you was, again, a bit simple, but it's just to illustrate what's happening within the learning process.
So that's all we've got time.
Okay.
Give a round of applause.